Welcome to Sri Learning Academy. Let's simplify monitors and synchronization. What if I told you there's a way to handle synchronization without constantly worrying about locks, unlocks, or forgetting to release something and breaking your entire system? That's exactly where monitors come in. And they feel almost like a relief after dealing with lower level tools like semaphores and mutexes. Up to this point, we've seen how processes or threads compete for shared data and how things can go wrong with race conditions if access isn't controlled properly. We also explored tools like semaphores, where you manually manage access using wait and signal operations. But the problem is, with those tools, the responsibility is entirely on the programmer. One small mistake, like missing a signal, can lead to deadlocks or inconsistent data. Monitors are designed to solve this by providing a cleaner, safer, and more structured way to handle synchronization. Think of a monitor as a smart container that wraps shared data along with the functions that operate on that data. Instead of letting any process directly access shared variables, everything must go through the monitor. This idea is powerful because it enforces discipline automatically. You don't have to remember to lock and unlock explicitly every time. The monitor ensures that only one process or thread can execute inside it at any given time. So, the moment a process enters the monitor, it gets exclusive access and others must wait outside. This eliminates a lot of common mistakes that happen with manual synchronization. It's like having a guarded room where only one person can enter at a time, and the guard ensures no one sneaks in or forgets to leave properly. To understand this better, imagine a bank locker system. The locker room is the monitor. Inside, you have your valuables, which represent shared data. Now, the bank allows only one customer inside the locker room at a time. You don't need to worry about locking the door yourself. The system already ensures exclusivity. When one customer is inside, others wait outside. This is exactly how a monitor behaves. It automatically enforces mutual exclusion, which was one of the key requirements we discussed earlier in the critical section problem. The difference is that now the system handles it for you, reducing the chances of human error. Now, just controlling entry is not enough. Sometimes a process needs to wait for a certain condition before it can continue. For example, imagine a shared buffer where one process produces data and another consumes it. If the buffer is empty, the consumer cannot proceed. If the buffer is full, the producer must wait. In semaphores, we handle this manually using counters and signals. In monitors, this is handled using something called condition variables. These allow a process to wait inside the monitor until a certain condition becomes true and then resume when it is notified. This makes the logic much clearer and easier to manage. Now, when we talk about processes waiting, there's actually a small but important detail to understand that there are actually two different waiting areas involved. First, there is the entry queue, where processes wait outside the monitor until they get permission to enter, since only one process can be inside at a time. But once a process is inside the monitor, it may still need to wait for a specific condition to be satisfied, and this is where condition variable queues come into play. Each condition variable acts like a separate waiting room inside the monitor, where processes can pause execution until a particular condition becomes true. Once the wait is over, the process actually heads back to the waiting line outside the monitor. Even though it's ready to execute, it still has to wait for its turn to be the one and only process allowed inside the monitor's boundary. So instead of one general waiting space, monitors organize waiting more precisely, separating those waiting to enter from those already inside but waiting for specific conditions. Let's take our classic printer example. Suppose we have a printer queue managed using a monitor. Multiple users want to send print jobs, but the printer can handle only one job at a time. Inside the monitor, there is a function to add a job and another to process it. If the printer is busy, new jobs must wait. Instead of manually checking and locking, the monitor ensures that only one job is processed at a time. If the queue is empty, the printer process waits. When a new job arrives, it signals the waiting process. This coordination happens smoothly without messy code. The programmer focuses on logic, not on low-level synchronization details. Another important aspect of monitors is that they combine data and operations together. This is similar to the concept of encapsulation in programming. Shared variables are hidden inside the monitor, and only specific functions can access them. This prevents accidental misuse. For example, if a shared counter is inside a monitor, no process can directly change its value. It must call a function like increment or decrement provided by the monitor. This controlled access ensures consistency and avoids unexpected behavior. If we connect this idea with earlier topics, especially the problems we saw in race conditions and critical sections, monitors act like a refined solution. Instead of writing separate code for locking, waiting, signaling, and unlocking, everything is packaged into a single construct. This reduces complexity significantly. It also improves readability. When someone else reads the code, they immediately understand that this part is synchronized because it is inside a monitor. Compare this with semaphores, where synchronization logic is scattered across the code, making it harder to follow. However, monitors are not magic. They still rely on proper usage of condition variables. If used incorrectly, issues like deadlock or starvation can still occur. For example, if a process waits but is never signaled, it will remain blocked forever. So, while monitors simplify synchronization, they don't completely eliminate the need for careful thinking. They just reduce the chances of mistakes and make the structure more organized. In real systems, monitors are often implemented through programming languages rather than directly in the operating system. Languages like Java provide built-in support for monitors using synchronized methods and blocks. When you use the synchronized keyword, you are essentially using a monitor behind the scenes. The language runtime ensures that only one thread enters that block at a time. This shows how important and practical this concept is, especially in modern multi-threaded applications. If we step back and look at the bigger picture, monitors represent a shift from low-level control to high-level abstraction and synchronization. Earlier, we were managing everything manually, like handling traffic using individual signals and instructions. Now, it's like having an automated traffic system that manages everything smoothly. This aligns with how operating systems evolve over time, moving from complex manual mechanisms to more structured and user-friendly designs. So, in simple terms, a monitor is a safe and organized way to manage shared data. It ensures that only one process accesses critical sections at a time, provides a clean way to wait for conditions, and reduces programming errors. As we move forward, especially into problems like producer-consumer or readers-writers, you'll notice how monitors make these solutions much easier to design and understand. That is it for this video. See you in the next one.